Welcome to a screencast on formal charge. In disinfecting solutions like chlorine bleach, the substance that does the disinfecting and sanitizing, so what you use in cleaning up in your house or what's used to keep pools nice and fresh and sparkling, the active ingredient is often a substance called hypochlorous acid, HCIO. And HCIO consists of a hydrogen atom, a chlorine atom, and an oxygen atom, but how could we predict the structure of molecules of hypochlorous acid? And the hydrogen, the chlorine, and the oxygen connect to each other, but is the chlorine atom in the middle of this molecule, or is the oxygen atom in the middle of this molecule? The hydrogen can't be, it's not going to form two bonds, but chlorine or oxygen could, and how would we predict which is the actual arrangement, which is the more likely structure? So if we consider the arrangement HOCl with oxygen in the middle of hydrogen and chlorine, if we do a Lewis dot structure, hydrogen has 1 valence electron, oxygen has 6 valence electrons, chlorine has 7. 1 plus 6 plus 7 is 14. So we put the 14 valence electrons for these three atoms around the atoms to form bonds and to fill or fulfill the octet rule around oxygen and chlorine. And we get an arrangement like this. And chlorine has 8 electrons around it. Oxygen has 8 electrons around it. Hydrogen, of course, will only have 2. Single bonds between hydrogen and oxygen and chlorine. And this looks like a pretty good Lewis dot structure. Now, what about the other possibility, HClO, with Cl in the middle? Well, if we fill in our electrons, 14 electrons as before, make bonds, we get octets. And here we have oxygen with 8 electrons around it, chlorine with 8 electrons around it, hydrogen with 2. That looks pretty good as well. So how would we distinguish between these two molecules? How would we predict which one is the likely arrangement in real molecules of hypochlorous acid? So both of these seem reasonable. They fulfill the octet rule. How do we make a prediction of the actual molecule? And in order to do this, we introduce a concept known as formal charge. This is a method that is used to differentiate when there's more than one Lewis dot structure we can draw that seem reasonable. And in this, essentially what we do is we assign a charge to each atom in the molecule and then compare that to the formal charges on atoms in the other structure, and then use a couple simple rules to make our prediction. And formal charge is defined as the difference between the number of valence electrons in a free atom, so the atom by itself, how many valence electrons does it have, and then we subtract from that the number of valence electrons that atom has when it's bonded. So it's the difference between the valence electrons in the free atom and the valence electrons in the bonded atom. And sometimes this relationship or equation is written as the number of valence electrons in the free atom minus half of the bonding electrons around that atom and minus the non-bonding electrons around that atom. And in practice, this is actually fairly straightforward to do, but if you look at this equation relationship out of context without trying it on an example, it's probably not going to be very clear how we do this. So to determine the better structure, we apply the following two rules. First of all, structures that have smaller formal charges are lower energy and more stable, and here by smaller formal charges we mean closer to 0. And if we have more than one structure that have similar formal charges in terms of how small they are, how close to 0 they are, then the structure that has negative formal charges on the more electronegative element will be the more stable one. And basically what these two rules indicate is that molecules that have atoms with pretty much the same number of electrons around them as they normally have, that's a good thing in terms of stability and low energy. And then if electrons don't have the normal number of electrons around them as they're used to, then it's better for a electronegative element, an element that likes electrons, to end up with negative charge around it than the reverse. So let's try this with our example of hypochlorous acid, and we'll remember the formula for calculating formal charge: number of valence electrons in free atom minus valence electrons in bonded atom. And there's our structure. And if we look at hydrogen, it normally has one valence electron. But now in the bonded atom, it has 2 electrons near it, but remember these electrons are shared. So what we can do is we can essentially sort of separate the 2 bonded electrons between hydrogen and chlorine and say this electron corresponds to hydrogen. So that's the valence electron around the hydrogen atom when it's bonded, and 1 minus 1 gives you a formal charge of 0 for the hydrogen. Now let's move on to the next element, chlorine. Chlorine normally has 7 valence electrons in the free atom, and as before, these 2 electrons are lone pair. They're definitely part of chlorine. These 2 are definitely part of chlorine. But these 2 electrons and these 2 electrons are shared between hydrogen and chlorine and hydrogen and oxygen. So what we could do is say, well, these electrons here are the ones that really belong to chlorine when we kind of split them between the 2 atoms. So chlorine has 2, 4, 5, 6 electrons around it, and so 7 minus 6 is plus 1, and so the formal charge on the chlorine is plus 1. And then last we have hydrogen to do. Normally we have oxygen to do. Normally oxygen has 6 valence electrons, but in this particular case it's got 2 plus 1 of the pair here, plus 2 more, plus 2 more. So it has 7 valence electrons around it in the bonded atom, and 6 minus 7 is minus 1, and that's the formal charge on the oxygen. So this seems pretty reasonable. We have reasonably low formal charges, 0 on hydrogen, plus 1 on chlorine, negative 1 on oxygen, and if we have to have a not 0 charge, then negative charge on oxygen is preferable to negative charge on chlorine because oxygen's more electronegative. So this seems fairly reasonable, but let's try the other one and see if it's any better or not. Okay, so next we'll do HOCl, and we'll go through the same process. Hydrogen normally has 1 electron around it. It has 1 of the 2 electrons in the shared pair, so it has 1 electron in the bonded atom, and that's a difference of 0, so the formal charge on the hydrogen is still 0. Now in oxygen it normally has 6. It has 2 plus 1 plus 2 plus half of that pair, so that's plus 1 more, so it has 6 valence electrons in the bonded atom, and that difference is 0 for the formal charge for oxygen. And then in chlorine it has 2 plus 1 of that pair plus 2 plus 2, so that is a total of 7 electrons by comparison to the 7 electrons in the free atom, and that difference is 0, so the formal charge on chlorine is 0. So let's compare our results now for HClO and HOCl. In HClO we had 0, plus 1, and minus 1, reasonably small formal charges, and a negative 1 charge on the oxygen, so that's not too bad at all. But in HOCl we had 0, 0, and 0, and those are even smaller than plus 1 and minus 1, and therefore, because this molecule, HOCl, has smaller formal charges overall, it is the better structure, and it is in fact the actual structure of HOCl, hypochlorous acid. It has a hydrogen bonded to an oxygen, bonded to a chlorine, and it has a bent molecular shape as shown here. And sometimes the formula is written HOCl, which shows the oxygen in the middle, the correct representation in terms of how the atoms bond, but it's also very often written as HClO, and so you can't always tell just by how the formula is written. But formal charges allow us to determine which is the better structure. And that's it for the Formal Charges Screencast.